now we're going to look at some examples of how the work kinetic energy theorem is used in problem solving. And before we get into the details of problem solving, the example that I have shown here for you, I wanted to talk a little bit about the language that's used and presented to you in questions and what to look out for. So the first thing you should always be looking out for is, does the question actually give you the initial speed and final speed of an object? If they do, so if the mass in the problem is known, and they give you the initial and final speed of the object, then you're done. The problem was essentially solved for you in the question because you know the work done equals the change in the kinetic energy, period. So if you know the change in the kinetic energy, then you know the work done. You don't need to go down the road of F dot delta X. And that was the next point I wanted to make. Sometimes they're going to give you in the question, especially up front, maybe the force information. So you're thinking, okay, they give me the force, I'm going to have to use F dot delta X. But nowhere in the question do they give you delta X, and it's not possible for you to calculate it. So what they're doing at this point is seeing that if you'll unlock from this F dot delta X mindset, because chances are in that question they snuck in the change in the speed of the object. Maybe they started it from rest, so that was v equals 0, and then told you something about its speed later on. Well, there you have the change in the kinetic energy. You know the work done. So they definitely will do that to you in questions, and you have to be on the lookout for that. The other thing, and specific to this problem, is when they're asking you the energy released specifically in explosions, you need to know that you have to focus solely on the change in the kinetic energy. So let's see what we're looking at here. We're told we have a 1 kilogram bomb moving with a speed of 20, and we're told that the explosion occurs, boom, and two pieces then, it's broken off into two pieces. The one piece is going to the left after the explosion at 70 meters per second. The second piece is going to the right at 50 meters per second, and we're told that the second piece is bigger at 7.75 kilograms, and mass 1 is 0.25 kilograms. Well, we have everything we need to know to calculate the change in the kinetic energy in this problem. So initially, the bomb was moving at 20 meters per second. That kinetic energy counts. We can't discount it. And that's going to be the crux of what sometimes is tricky about these problems. So that kinetic energy counts. It had 200 joules of energy. So that bomb carried 200 joules of energy even without the explosion. Once it exploded, now we have the total kinetic energy after the explosion given by 1/2 m1v1 squared plus 1/2 m2 v2 squared. So we're given all the numbers to plug in, so we can see that after the explosion, in total, there was 1,550 joules of energy, but 200 of those 1,550 was already there. So when you want to actually state the energy that was released in an explosion, you will always calculate the change in the kinetic energy, and you have to subtract off any kinetic energy that was just part of the motion of the object to begin with. Okay, one final example that I want to talk with you about, and that's looking at what gravity does specifically to an object in free fall. So these problems have appeared on multiple back AP tests, both as multiple choice questions and as part of free response questions. And what's really important, anytime you're looking at the energy transferred to a mass by gravity, you absolutely have to pay close attention to what they're giving you to plot on the y-axis and specifically on the x-axis. So in this case, if you were asked to graph out the general shape of the work done by gravity, the energy transferred to an object by gravity, as a function of time, as an object is falling. Well, that can be a little tricky just to think of, try to think of the answer in your head without actually analyzing what's going on. What is going on is that the object is in free fall, so that the only force acting on it is gravity, mg down. And the delta y, it's in free fall going down, so free fall could be going up, but in this case we're saying falling. So we get cosine of 0, we get mg delta y. It's still undergoing constant acceleration, so I can look at the constant acceleration equations, delta y equals v initial in the y direction times time plus 1/2 at squared, to see that the work done by gravity is actually quadratic because of the t squared here. So that's why we have this drawn as a t squared graph. And if you were to explain it in words, you would explain the calculation over here that it's actually quadratic with time. Now, why are we showing that the work done by gravity is linear here? And the only reason we're showing that it's linear is because, look, they're trying to trick us. They gave us t squared on the x-axis. So if we go back and look at our equation that we just derived, the energy is directly proportional to t squared. So you get a linear increase. And the last one I have to show here is velocity. And if they were asking about the work done by gravity relative to the speed of an object, work kinetic energy theorem. Since the work done by gravity of an object in free fall will equal the change in the kinetic energy of the object, the work is proportional to v squared, so we get our quadratic when we're plotting it with respect to v. And I ran out of page here to show you a final linear graph, but I hope at this point you can see how that game is played, that had they given us a v squared down here, that graph would be linear because the work is going to be directly proportional to v squared. Okay, that's it for our examples of using the work kinetic energy theorem for the notes, but certainly we have more of these to do, these types of problems to do in the homework packet.